problems. Okay, here we have a structure with the formula C9H10O2, and here's our NMR data. So instead of giving you a spectrum, it's presented to you, just in numerical form here. Okay, and the problem with NMR that I see again and again working on NMR problems is there's so much information. You could just get blown away by that information, and it's very easy to spend 30 minutes working on an NMR problem and go nowhere because you just are grabbing at bits and pieces. Okay, so we're going to develop a systematic approach. We're going to use that same approach every time, and we're going to hopefully find success in that approach. Okay, so what was our first step? Our first step is to look at the IR spectrum and see what we can figure out from that. But we're not going to be looking at any IRs today. A lot of the problems you're going to see in your courses or in the books will have IR combined with NMR, so that you're lucky in those cases you get that as an additional clue of what functional groups you have. But in all these cases, we're going to be skipping the IR. Okay? Do we have a molecular formula? You won't always be given a molecular formula, but if you're lucky enough to get it, let's use it. So we do have a molecular formula. It's C9H10O2. What can that tell us about the structure? What we need to do is we need to calculate the DU. Okay, the way we calculate the DU is we ask ourselves, if it was saturated, what would the formula be? We have 9 carbons. It would be C9H to the, remember it was C to the N, H to the 2N plus 2. So it's 9 times 2 is 18, plus 2 is 20. If it was saturated, it would be C9H20. What do we have? We have C9H10. Okay, so what do we have? We have 10 missing hydrogens, and every 2 missing hydrogens is a degree of unsaturation or a site of unsaturation. So we have 5 DU. So our formula, when we're done, has to account for all 5 of those. Okay, now what do? We figure out what pieces we have to our puzzle. We use the integration for that. So we have 5 hydrogens here, somewhere around 7. What piece does that tell us? What thing's coming around 7? That would be aromatic protons. We have 5 of them, so that tells us that we have a monosubstituted benzene ring. We have a benzene ring with 1 something hanging off of it, attached to it. Okay? We have a 2 hydrogen signal. What does a 2 hydrogen signal mean? It means we have a CH2. And when I draw this piece, look what I'm going to do. I'm going to draw 2 arms on it. And that's because we know every carbon is going to have 4 bonds in our structures when we're done, because we're only looking at stable, stable structures. So a CH2 must be attached to 2 other things to get those 4 bonds. And what does a 3 hydrogen signal tell us? That means we have a CH3. A CH3 has just 1 arm, because that would be the 4th bond. So these are our pieces. Are they all of our pieces? Well, what do we have so far? We have C6, 7, 8. We have C8, H, 5, 6, 7, 8, 9, 10. Okay, so we've accounted for all of our hydrogens, of course, because they show up in their NMR. It's hard to miss those. But we only have 8 carbons shown, so we still have a carbon. We still have 2 oxygens that we need to account for. Oxygen has 2 arms, right? Oxygen likes to have 2 bonds. And what else are we missing? Let's check our formula. Our formula says we need 5 degrees of unsaturation. How many have we shown so far in these pieces? We've only shown a benzene ring, which has 1, 2, 3, 4 degrees of unsaturation. So we still have 1 degree of unsaturation that needs to be in our structure when we're done. Now this looks like a lot of random pieces, but take a look at this. There's actually a very nice functional group we can imagine that takes care of all 3 of those. What is a way to have a carbon and an oxygen with a degree of unsaturation? How about a carbonyl? A carbonyl would very nicely account for all 3 of those pieces in one nice, functional group that we see all the time. Carbonyls are very, very common in organic molecules. And of course, a carbonyl has 2 arms. Okay, so these now are our pieces. So we've taken care of this. So we have a phenyl ring, CH2, CH3, carbonyl, and an oxygen. Those are our pieces. Now we're ready to put them together. We start with an end piece, and we decide what it's attached to. So let's start with our CH3. what are our choices? We could either attach it, could we attach it to the benzene ring? We can't attach it to a benzene ring because that's an end piece. If we attached a methyl and a benzene, we would now have toluene, our structure would be done. We couldn't fit in any of the other groups. Okay? But I could attach it to a CH2 or an oxygen or a carbonyl. Those are the other possible pieces. How do I decide which one it belongs to? Well, now I take a look. Where's my CH3? I take a look. It must be a singlet. So what does that rule out if it's a singlet? Singlet means that I have 0 neighbors, right? I have 0 protons on my neighboring carbon. So I can't attach it to the CH2. That would split it. But it could be the oxygen or the carbonyl. How do I decide which one it is? Well, I take a look at the chemical shift. Is that the chemical shift I would expect when I'm next to an oxygen or when I'm alpha to a carbonyl? That means I'm alpha to a carbonyl. If I put it next to an oxygen, that brings me too far downfield, brings me closer to 4. So I must have this attached to the carbonyl. Okay, that took care of this piece. That took care of this piece. What comes next? What are my options? I can either have an oxygen or I can have a CH2. Okay, now it turns out in this case, let's take a look at that. Let's put the oxygen first and then the CH2. And then the last piece I would have is the benzene. Or the other possibility, we're down to just 2 possible structures. We could have the CH2 and then the oxygen. Okay, and we can use, would that explain the chemical shift and the splitting pattern for the CH2? It would actually, because this is a singlet, which is true in both cases. And it comes at around 5. How does it get all the way to 5? Well, it's both next to an oxygen and it's next to something else. In this case, a benzene ring. It's benzylic. In this case, next to a carbonyl. So actually, both of these answers are reasonable. The way I would distinguish between the two of them, if I had some tables, maybe I can calculate it a little more precisely to see which one best matches 5.1. But the other thing that I would recognize if it's a little more sophisticated, is I know that having an oxygen on a benzene ring is going to have some resonance, which is going to make some of these protons much different, give them a much different chemical environment, electronic environment, than the others. So because it is a 5-hydrogen singlet, I'm expecting all these hydrogens to be very similar and therefore just attached to a regular CH2, and so this is the best match. This is the best match. Occasionally, we might have a case where there's more than one possible answer, but that's pretty. This is a pretty rare situation. Okay, let's try a different one. Turns out we have the same formula, and we have the same pieces. So just like we did our process before, we would find that we have 5 degrees of unsaturation. So we have a 5-hydrogen aromatic signal. We have a CH3. We have a CH2. We have a carbonyl. And then we have an extra oxygen. Same 5 pieces as we did in the previous problem. How are we going to put them together? Well, again, let's start with our methyl group. Let's start with this end group. Tell me about this methyl group. It's a singlet, again, so it has the same splitting pattern as before, but now it's at 3.6 ppm. So which piece would make sense to attach to the methyl that would bring it to 3.6? This would bring it to 3.6 if we put an oxygen next to it. Okay, so that takes care of our oxygen and takes care of our methyl. What do we have next? Or what other pieces can we put together? Well, let's think about our CH2. What is our CH2 going to be attached to? Our CH2 is at 3.5. Okay? So if we put, let's think about our possibilities. If we put that here, if we put our CH2 next, we would expect that to be at 3.5, just like the first one. But then when we attached it to another piece, the carbonyl or the benzene ring, what would happen to that 3.5? That would de-shield it even more, and we wouldn't expect it to be there any longer. So we can't put the CH2 here. Instead, it's the carbonyl and then the CH2. So don't be afraid to look at your options. Rather than have it all swirling around in your head and trying to imagine all the possibilities, just write out the two possibilities that you're considering and then see which one fits the data best. Okay? Right? So what I'm saying here is if this were the carbonyl, if we looked at this option, then this would be much more downfield. This must be higher than 3.5. Okay, but now if we were to predict this, where do we expect this to be? Well, it's going to shift a little downfield because of the carbonyl, and it's going to shift a little downfield because of the benzene ring. That would put it at 3.5. 3.5 ppm is very reasonable for this one. We would expect it to be a 2-hydrogen peak. Is this a singlet? It is a singlet, just like we predicted. I went through this a little bit on the previous one, but we want to make sure that we double check our work. This CH3, what do you predict for that? Its splitting pattern would also be a singlet. And where do you expect it to occur? What would its chemical shift be? It's attached to an oxygen. So again, 3.8 we would expect here. It's 3.6. That makes perfect sense. These hydrogens all are 5 hydrogens around 7. In this case, 7.4. Okay, so we can propose a structure and then double check it, and we know we have the right answer.